Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at the start of Chapter 19. So we'll cover Chapter 19.1, just a little bit probably of 19.2. On the AP test every year, the thermodynamics ideas, which we've already done a little thermodynamics earlier in the year, so this is really coupled with back in around Chapter 5. The multiple choice portion typically has around 4 questions from the thermodynamics chapter, and FRQ, pretty much every single year there will be something related to thermodynamics. Now, first law of thermodynamics is where we'll start with, and you'll recall from Chapter 5 that energy cannot be created or destroyed. Therefore, the total energy of the universe is constant. This would be an expression of the first law of thermodynamics. Energy can, however, be converted from one form to another or transferred from a system to the surroundings and vice versa. Now, spontaneous processes are those that can proceed without any outside intervention. The gas in vessel B will spontaneously effuse into vessel A. So once we open up the valve, it will spontaneously effuse, but once the gas is in both vessels, it will not spontaneously return back to vessel B. So it's spontaneous in one direction, but not spontaneous in the other. Processes that are spontaneous in one direction are never spontaneous in the reverse, so they are always non-spontaneous in the reverse direction. Processes that are spontaneous at one temperature may be non-spontaneous at other temperatures. Above 0 degrees Celsius, an example of this, it's spontaneous for ice to melt. So when you take an ice cube out, if it's above 0 degrees Celsius, it's going to spontaneously start to melt. Below 0 degrees, however, the reverse process is actually spontaneous. So really the spontaneity of this particular reaction depends upon the temperature. But notice, in both cases, when one direction was spontaneous, the other would not be at that temperature. Now, in a reversible process, the system changes in such a way that the system and surroundings can be put back in their original states by exactly reversing the process. That's really the key to spontaneity here. Or I should say, that's a key to reversibility. It's a reversible reaction if you can exactly undo what you did and get back the original situation. Now, reversible processes are those that reverse directions whenever will reverse directions when an infinitesimal change is made in some property of the system. So at the case of equilibrium, remember we talked about ice a second ago. Above 0, it was spontaneous to melt. Below 0, it was spontaneous to freeze. Well, at 0, you're basically at an equilibrium situation between the two states, and with just a little bit of energy, it will start to melt, remove a little bit of energy, and it will start to freeze. Exactly undoing the addition or removing of heat causes it to switch directions. So that would be an example of a reversible reaction. So the equilibrium reaction of ice at 0 degrees, add a little bit of energy, it melts, remove a little bit of energy, it freezes. That would be an example of a reversible process. Irreversible processes cannot be undone by exactly reversing the change to the system. And that's what we've got here in this little piston setup that we have here with a removable partition. So we've got, in the first situation here, a vacuum in this part, a gas in this part, and a partition between the two. Now, if we remove the partition, the gases will diffuse spontaneously throughout. But remember, spontaneous processes are reversible. When the barrier is removed, the gases spontaneously expand to fill the evacuated space, doing no work on the surroundings. So our work situation here is 0. To get back to the original state, you can't exactly reverse the process. Work must be done on the system by literally pushing it on that piston to get it back to its original state. So it's irreversible. So in this particular situation, we have a spontaneous reaction. We remove that partition, it's going to spontaneously disperse, but this is not a reversible reaction because we can't exactly undo. If we just take and we slide that back into position, that would be exactly undoing what we did. We don't get back to our original situation. So this is not a reversible situation here. Now, we're going to do a little bit of section 19.2 before we stop. Now, 19.2 gets into entropy and the second law of thermodynamics. Now, entropy, which is a term you should remember from pre-AP chemistry if you took honors, because we do a little bit with entropy in that chapter. We basically introduce the idea and touch it just a little bit. Here we're going to expand on it quite a bit in this chapter. Entropy has the symbol S, and it's a term coined by Rudolf Clausius in the 19th century. Now, Clausius was convinced of the significance of the ratio between the heat delivered and the temperature at which it was delivered. So this ratio of Q, the heat delivered, versus the temperature. So he thought that this was a significant term. Now, entropy, that term will come back in a second. Entropy can be thought of as a measure of randomness of a system. So the degree of randomness is one way to look at entropy. Now, this is really only one aspect of entropy, but in many situations on the AP test and on my test, if you take a look at the situation and you determine, well, in which situation would it be more random, you can often figure out whether entropy is increasing or decreasing. So this is a simplistic way to look at really what entropy is. It's the measure of randomness. So the more random it is, the higher the entropy is. Now, it's related to various modes of motions of the molecules. And this is something that section 19.3 gets into a little bit here. So if you take a look at what's happening, are we increasing our modes of motions of the molecules? Then we're going to be increasing the entropy. Like total energy, which is E, the enthalpy change, which is H. Remember, E and H, we had delta E and delta H because they were state functions. Well, if entropy is also a state function, that means it's independent of path, and we can derive an equation. The change in entropy would equal the absolute entropy under our final conditions minus the absolute entropy under our initial conditions. So what is our final entropy value minus what is our initial entropy value? That can give us the change in entropy. And that's what we're usually looking at, is the change in entropy. For a process occurring at a constant temperature, which is known as isothermal, same temperature, the change in entropy is equal to the heat that would be transferred if the process were reversed, divided by the Kelvin temperature. Remember what Clausius was looking at? Shortly, he was thought that the ratio of Q versus T was a significant value. Well, that's because it's related to the change in entropy. Now, units of entropy would then be joules per Kelvin. So keep that in mind. When you're dealing with delta S, you should always get joules per Kelvin. The second law of thermodynamics states that the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for a reversible process. This is one aspect, or one way of expressing the second law of thermodynamics, dealing with the entropy of the universe increasing for spontaneous processes. So in other words, for a reversible process, the change in entropy of the universe would equal 0. Remember the system? This is an equilibrium system situation. So if it's a reversible process, you're at equilibrium, and your change in entropy would equal 0. But if it's an irreversible process, the change in entropy is always going to be greater than 0, which means another way of expressing the second law of thermodynamics is that the result of all spontaneous processes is that the total entropy of the universe is always increasing. So this is really another way of saying the second law of thermodynamics, which is to say the entropy of the universe is increasing. So for irreversible reactions, the entropy will be increasing. For reversible reaction, the entropy change would be 0. So overall, when you look at all the different reactions that occur, there's going to be net increases in the universe in entropy. And that's where we're going to stop today. So it was a nice short set of notes to start Chapter 19.